All right, great. So thank you for having us here today to talk about a framework to support data fusion analysis and decision-making projects. Sean and I worked with a few other folks on this project for the Federal Highway Administration. And today we'll walk through that research and the outcomes of that research. So first, just a brief disclaimer that this is a presentation that we've created as contractors for the project, and it doesn't necessarily express the views of the FHWA and so on. So this is a necessary disclaimer that we need to include here. So in terms of introduction for this project, the goal of the data fusion framework was really to support decision making by reducing human error, institutionalizing data fusion processes to improve that decision transparency, and then really to maintain the stability when it comes to data-driven decision-making. And that stability comes from retaining that institutional knowledge, improving that transparency, reusing data projects and so on. So again, the idea here was to establish a framework that would allow for all of these benefits to manifest themselves with any agency that implements this framework. So in terms of the impact of this framework, the key impacts include tying the lower level operations decisions and actions with the upper level goals and objectives. So again, it's kind of crossing different boundaries within an agency at different level, and then providing these connections allows the framework to enable agency managers to visualize these impacts and adjust their decisions based on new insights from data fusion processes. So again, taking different data sets, performing the analysis and the fusion of these data sets, and then using the outcomes of those analyses across different levels of the agency to inform their decisions, both from an operational, tactical standpoint, as well as more strategic operations standpoint. So in terms of the target audience for this particular framework, it supports many different groups within a DOT, as well as the outside stakeholders, information technology staff, partnering organizations, and so on. It's applicable across multiple levels of the organization, as I mentioned, from TMC operators, emergency management, et cetera, to executive management. But then it's also bridging the gap between operations and IT and system integrators and developers as they develop the systems to support operations using data and data fusion. So again, the goal is to bridge those gaps and allow agencies to capitalize on their data investments on all different levels of the organization. So briefly, on a high level overview of this framework, it consists of 5 major sequential steps. Each step has multiple sub-steps in it. And in the report that we built for this framework, or in the framework, you can actually go between different steps and sub-steps and orient yourself in terms of where you are in the framework and where you need to go in the next step of the framework. Now, these steps are sequential, but at the same time, not all of the sub-steps will always be relevant. And so different use cases capitalize on different areas of this framework. And therefore that framework is flexible enough to support multiple use cases and scenarios. And then it also has a feedback loop, as you see from the evaluation step back to analysis step to evaluate those results and improve the future decisions. So on a high level, it's a 5-step framework with more detailed sub-steps within that framework. Now, briefly to talk about the difference between analysis tools and methods, we want to clarify the relationship between these two things because it might be of relevance to implementation of the framework. And there are tools out there that help prepare, clean, analyze, and report data, but it is useful to understand the underlying methods that the tool may be executing to achieve those goals. So in this example, we're thinking of the tool as a car that is powered by those methods, which is the engine of it. So again, the tools and the methods are delineated in this framework so that we understand the underlying work that needs to be done to make those tools effective and the outcomes useful. All right, so moving into the actual framework here, I'll walk through a few steps of the framework before I turn it over to Sean. The first step of the framework is to ingest data. So what we've done is we define 7 different categories of data, and you can see them listed here. These are fairly broad categories that consist of many different types of event and incident data and traffic performance data and so on. And what we've found in the framework is that the single category fusion is useful if you want to improve quality of information. So fusing data within a single category might be taking the same type of data from multiple sources, or maybe with different properties, and then putting it together and determining, exposing maybe the more accurate data by looking at multiple data sources and so on. However, if we look at multi-category fusion, that can actually bring additional insights and benefits, because we're combining data and information from different sources as well as of different types to get a more comprehensive picture of what's happening out there. And so there are different types of benefits of combining these data sets, as well as some of the drawbacks of treating data as information. Those are 2 separate things. And so we in the framework, we talk about how, as you ingest this data, you have to think about these different data types and how they would fit into different categories and implications for the fusion. I went the wrong way here. Traditional data and information tends to be well defined and structured. This is as we were starting to collect more data out on the roadways. A lot of it came from sensors that were specifically calibrated and provided only certain small sets of data. And so in the past, we were able to manage that data using traditional relational databases and extract and transform and load processes. Just because this is a traditional approach doesn't mean that it's not important and relevant. It's still important and relevant. But as we are getting more data from more different sources, it is important to understand that the big data that's out there today may involve different approaches to it, and involve things like sampling and streaming, also using the non-structured data storage and processing systems, because the data might not be well structured. For example, if you get something that's coming from a crowdsourced data source, then it may have a different form and not be able to be fit into a standard relational concepts. One of the key things in this first step of ingesting data that the framework advocates is storing data at the lowest possible granularity. This is important because if data is overly granular, you can always roll it up or aggregate it to a level that's needed for a particular application. However, it's a lot more difficult to go the other way around. If data is not very granular, trying to expose some of the more nuanced information out of that data may be difficult or impossible in some cases. So the goal is to ingest data at the lowest possible granularity to support different use cases. In the second step of the framework, we take data that we've ingested and we start the process of cleaning that data. And cleaning that data includes assessing the quality, tagging it and cleaning it, and then doing some initial fusion. So on this slide, you're seeing a number of different data cleaning checks and actions that are taken. So for example, presence. Are there entire expected records that are missing out of the data set, and how do we handle that? Completeness, are there some elements within that data record that are not available? In terms of uniqueness, this is especially the case if we're looking at multiple sources. We may be getting the exact same data, and so this data may already be present in our system from somewhere else. From a consistency standpoint, it's just looking at this data and saying whether or not it makes sense. So maybe it goes through all of the error checks and the numbers are all good, but do they really make sense? That's the consistency piece. Range constraints, so that's more of a standard checking of the boundaries for a particular value. Error checking, standard validation. So if somebody's claiming that the data isn't a particular standard, Is it really validating to that standard? And so on and so forth. So these are all the different steps that you can take within the cleaning step once you ingest the data to utilize it. And then as you do that cleaning, you move to that fusion piece, and the true value of this data really is exposed once you start fusing it, either with similar data sets or disparate data sets. So the goal of the fusion is to improve the quality of the data set and or to extract new information that may not be available from a single data source. And there are several elementary data fusion types. For example, there's spatial fusion, which is where we match things based on their spatial extent. So maybe it's looking at event data matched with TMC code, the traffic message channel code, a link on the road, for example. Temporal, again, looking at data that's temporally close to each other. So maybe it's a sensor data set with an event data set or with some other data set around the same time and spatially around the same location. Complementary, redundant, and cooperative are three other types of data fusion, elementary data fusion that allow these different data sets to either complement each other or maybe validate a particular, in terms of redundant, validate that the speed coming, for example, from probe data is matching the speed coming from a loop detector. And so it's validating the ground truth. And similarly, cooperative, where we're looking at two different data sets indicating maybe the same type of an event happening out there. So in this case, weather data, looking at that versus connected vehicle traction control activation and saying, yes, we know that there's ice here and traction control data is showing us that it's being activated in this location. Therefore, these are kind of a cooperative data fusion approaches. All right, so step 3, I will turn it over to Sean.
Thank you, Nicola. Good afternoon. So Nicola already described at the very high level how we can process the data, fuse the data. So now imagine that you have all the data all lined up, right? They all add up in the same row segment with all different type of incidents, speed, counts, whichever data you choose to use. It's all lined up right now. But the ultimate goal for any sort of applications of these data fusion techniques is really to go to decision making, right? We want to get as much of insights as we can, and also make any sort of decision making, make the best use of the data. So next few steps is really a few steps about analyze, about decision making, about reevaluation, feedbacks. So these are step 3, 4, 5 that I'm going to talk very briefly at the very high level. Then I will go back to give a couple examples and one particular case study. Then I will hand back to Nicholas to present another study and for this for the whole research report. About analysis, this is step number 3. Once the data is all fused geographically or temporally, then we want to apply some sort of methods either to visualize, to extract some insights, not necessarily to make any decision yet, but this is the step for us to get some understanding of the system dynamics. For example, if we know the current speed is 25 miles per hour, maybe you want to analyze the data to see, hey, historically, is this really above average? Is it below average? Not necessarily making a decision yet, but this is a very essential step that we are going to apply some of the statistical models or AI machine learning models of our choice. It can be very, very simple, as simple as, hey, we can set up a rule, expert rule, anything beyond 25 miles per hour will be anomaly, right? As simple as a rule. It could be also as complicated as we apply very sophisticated machine learning algorithms, supervised learning, for example, just to use 10 years of data, learn everything whether we just fused from history and then to set up certain rules that comes from machine. So anyway, this my point being, this is really applications or analysis that we try to understand the system better before we even make any decisions. And Nicholas, next page. Right, here's another example. This is the example for the unsupervised learning, namely clustering. Imagine that we have all the data, row segments, time of day, season, weather conditions, incidents, work zones, And then this is just an example showing if we fuse all the data together in the same geographic zone, maybe in a year, or maybe depending on, again, the temporal scope of your choice, we can do some clustering analysis, really saying, hey, this is a typical winter Wednesday sunny day, or this could be a typical atypical summer humid day with a crash on highway X, Y, and Z. So once we cluster, this is what we call typical pattern. Once we have it, and then we can develop, right? We know this is a typical pattern, and we can develop a specific response plan. Namely, the next step is really the decision making for each specific pattern. Next page. And I want to talk a little bit about the AI machine learning, and then this is kind of very can go really sophisticated, but oftentimes the machine learning part is really applies to analysis. It's really about, it's part of AI, but it's not entirely AI. Machine learning means that we want to apply statistical models and machine learning algorithms to understand the system dynamics. Like I said, we only wanted to understand the system, but before we make any decisions. Nicola, next page. Yes, and AI is really about the whole process, starting from the fusion all the way to the end of making any recommendations about decision making. This is the whole process. We try to automate the process. Of course, machine learning is being part of it, right? Next step. Right, so this is again a graph about depending on what type of problem you're addressing, depending on what kind of data available to you, depending on your comfortable zone about how sophisticated the model want to be. And then depending on many different criteria as we listed here, the problem solving can, and then the kind of data you use can go from very simple to medium to very powerful tools. And then that really also corresponds to is this really a quick and kind of dirty kind of planning, or this is really you want to go as much granularity as you can about the micro simulation or micro level management, and then accordingly you're going to use different data fusion methods as well analysis of decision making methods. Next page. And the step 4 is about decision. Once we learned about system, for example, we predict the system is likely to going to have anomaly in the next 25 minutes. And we know the system, now it's time for us to make a decision. So this decision, there are many different types of decisions we can make strategically, tactically, and operationally. And there are also different methods that we can use. Ideally, we want to, that's what by the name of AI is that we want to automate everything, right? And then without really having any human to intervene the system, which is oftentimes what we think is not so ideal, because we really want to have a lot of expertise from the professionals who can see the real system conditions and to intervene the system at the time we need. But having some sort of intelligence from the machine that we can learn from the past and automating the process in the way that keep human in the loop, and then making sure the system doesn't go wrong is really what we recommend. But we do have different levels of engagement of the data fusion and then decision-making process, automated operator, entirely human, and human in the loop are 3 different things. Next page. Okay, so the step 5 is about assessment. It's really important that everything we just talk about is analysis and decision making. We start from somewhere. We have to start from somewhere, and not necessarily learning about the optimum of the system. And then we do, because we have the data. Again, this is also being part of the data fusion, is that after we engage the system, after we're making some kind of decision, and post the decision, it's really crucial for us to collect the data again, the same data you just fused to make any decision, just to see, hey, well, does it really meet my expectations, and how does that thing, the KPI changes over time? Are we really making the good decisions? If it's a bad decision, can we go back to the step 1, 2, 3? To engage different sets of data, or maybe we find there are biases in the data, we want to go back and change it and correct it. So this is another step that we are talking about, that essentially we need to have some kind of feedback loop to improve the whole process over time. Next page. So this is really about the just line up the step 3, 4, 5. This is about analytics part of it. Again, I try to emphasize we can look at this whole process at the strategic level, tactical level, where you go change the program, change the investment, capital investment, but can also get at the very operational level. You can tune the signal timing, give feedback, and to improve the system, change different clusters, and develop a different response plan for each class, and etc. Next page. So I'm going to very quickly present 2 case studies. One is a data fusion and decision-making case study we applied to Cranberry Township Traffic Management Center. And then Nicola will talk about another case study implemented in PennDOT. Next page. And this is a very kind of a real world operation. And the idea is very simple. Now all the traffic management centers, I'll give you a little bit of background. Cranberry is a town roughly about 25 by 25 mile area. But what's so unique about this township traffic management center, why it's so challenging, is because it sits in the intersection of one turnpike, one highway, interstate, and then 2 state route. Very busy traffic, and anything go wrong, that's what they call doomsday, right? So if something goes wrong, any of the 4 highway segments, and then the whole township and will get into the gridlock. But now the reality is that they have a lot of data, cameras, Ingest data, speed counts, incidents report, 911, 311, everything. But the data could be very, very overwhelming. How can we translate the data to some sort of decision making as early as we can? Because in these traffic management center, I think the timeliness and then the being proactive rather than reactive is always the key. You want to get ahead of the time when you see there's a congestion. So the goal here is trying to, hey, look, we have all this data. Can we fuse them and then analyze them and then make proactive and ahead of the curve decisions as early as we can? Next page. And then that decision will send automatically, right, 24/7 to the traffic management center staff. And what we do is the details in the report, but I think the very high level, we fuse the weather, incidents, crowdsource data, Waze, and social media, travel speed, PennDOT incidents data, state data, and then we use the machine learning model to train it about 2 years of data, and then make the predictions, set up certain rules, and alert the traffic management center 24/7 about, hey, something's going to happen is going to happen in next 30 minutes. Maybe it's time for you to start to engage signal timing and contingency plan X, Y, and Z. And then we also tell them when to stop, and then if we anticipate the queue will dissipate very quickly. Next page. So some of the very brief performance metrics, when we talk about the evaluation, we do in the past 2 years, 3 years actually, the system has been deployed in the TMC, and we do see that traffic congestion under incidents has been reduced quite substantially. We also see that, and oftentimes the system with the data fusion, because the data give us a lot of information about predicting when this anomaly is going to happen, and then we're able to get ahead of the curve roughly about 15 to 25 minutes earlier than a Waze report. And everything is automatic and then 24/7, and that's only a message away. Next page. Okay, Nick, I hand over back to you.
All right, thank you, Sean. So I will briefly talk about the PennDOT use case that Sean mentioned earlier. So in this use case, PennDOT has developed a congestion causes dashboard. The idea behind this dashboard was to fuse multiple data sources and create a dashboard that would be informing the operations at different levels of the organization. And so what they've done, similar to what Sean described with the Cranberry Township, weather data from different weather stations and traffic applications, as well as data related to speed and congestion. This was coming from the private sector data provider, and then event data from multiple sources. So they had data coming from traffic applications, police records, probe data, and their own incident data. So they were fusing these 4 categories or 4 types of data, but within those sets, there were multiple sets as well. And they were using some of those elementary data fusion methods that I mentioned earlier in terms of temporal, spatial, redundant data fusion. And so what they've done is they've developed a dashboard, and this is an example of that dashboard on the right side of the screen, that allowed them to expose a lot of different insights. So first, they were able to identify when and where the congestion was occurring. They were able to do this in real time, and they were able to look back at different time periods as well. And then they were also able to assign confidence scoring for different data sources. So as I mentioned, not only were they utilizing multiple data sources, they were able to provide more information about which data source may be reliable in which particular case. It's not that one data source is always more reliable. It could be that different use cases warrant different type of weighting. And then they were also looking at congestion causes for those events. So whether they were happening because of weather or is particular event occurring, or if it was a recurring congestion type of a thing. And then they were also looking at all of this in near real time in terms of regular schedule, where they were able to update this congestion, this causes of congestion dashboard, and then also use the information that they've collected and fused together to plan for some of the bigger events. So in terms of the utilization of this dashboard, as I mentioned, planners used it to justify some of the investment decisions. So they were able to look at things like user delay cost as it pertains to different sources of those delays. So in this case, you can see graphics here for 12% of the user delay costs are due to incidents versus 2% for work zones and so on. Now, they are not using this in real time necessarily. As I mentioned, it's kind of a regular near real time dashboard updates. But the goal here is to start adding additional data sets to boost the information in or allow decision makers to have more information to work with. So for example, using trajectory data for signalized corridor analysis and things like that. In this case, you can see that user delay cost is 17%. In this particular case was caused by signals. So understanding a lot more about how signals are contributing to those user delay costs are the goals for this dashboard. What was great about this is that the success of PennDOT use case has been inspiration for other agencies outside of PennDOT to start to create similar tools and utilize them for their operations decision making. So that's the PennDOT use case that covers the brief summary of the framework and the project. The report is available out there. We can take questions now. I don't see any open questions in the chat, but I will also put James. I know he's in the call as well. This is his contact information if you have any questions after this meeting as well.